When a backyard telescope outperforms Hubble, you pay attention. Paul Craggs just released an image of 3i Atlas that shows something professional astronomers either cannot see or will not talk about. This is not the blurred, dusty comet in the official photographs. This is a clean, structured object with defined edges, a brilliant white core, and a blue glow that wraps around it like an energy field. Comets are chaos. They fragment, they shed gas, they blur into clouds of dust. This looks controlled, deliberate, almost artificial. NASA says comet. The image says otherwise. Tonight we dissect the data from both sides, examine the anomalies no one wants to address, and confront the possibility that 3i Atlas is not what we have been told. Stay until the end, because the implications of this photograph are about to get uncomfortably real. You'll want to stay close as 3i Atlas continues its journey through our solar system and the data keeps rolling in. Subscribe and follow along, because every new observation brings us closer to understanding what we're actually looking at here. Now, let's dim the lights and dive into this cosmic mystery together. A backyard astronomer named Paul Craggs pointed his Dwarf 3 telescope at the sky on a clear November night in 2025 and captured an image that should not exist. He was tracking 3i Atlas, the interstellar comet that's been making headlines since its discovery earlier this year. He expected what everyone else had been seeing: a fuzzy blob, maybe some dust, the usual mess of ice and rock that comets throw off when they get close to the sun. What he got instead was something clean, sharp, structured, a brilliant white fuselage with a smooth, almost artificial blue glow wrapping around it like some kind of exhaust plume or energy field. This is not what comets are supposed to look like. Comets are chaos. They are dirty snowballs, crumbling ice mountains that shed dust and gas in wild, unpredictable patterns as they tumble through space. They break apart. They fragment. They look messy because they are messy. But this image shows none of that. No diffuse cloud, no scattered debris field. Just a defined, almost engineered shape with a color and clarity that makes you do a double take. When Craggs posted this image online, it detonated across amateur astronomy forums and niche science communities within hours. People were stunned. Some called it overprocessed. Others said it had to be an artifact, a glitch, something wrong with the sensors or the stacking software. But then more images started appearing from other amateur observers using similar setups, and they were seeing variations of the same thing. An object that looked far too organized, far too symmetrical, far too clean to be a natural comet. The excitement was immediate and electric. If this is real, if this is what 3i Atlas actually looks like, then we have been fundamentally wrong about what we are dealing with. Craggs is not some wild-eyed conspiracy theorist with a grudge against NASA. He is a skilled astrophotographer with years of experience capturing deep sky objects. His equipment, a Dwarf 3 telescope, is good but not extraordinary. It is the kind of gear that serious hobbyists use. It is not Hubble. It is not the James Webb Space Telescope. It is a small, consumer-grade telescope sitting in someone's backyard, and yet it managed to resolve details that billion-dollar instruments either missed or chose not to emphasize. That fact alone should make you pause. How is it possible that a modest telescope on Earth captured something so dramatically different from what the most advanced space observatories have shown us? The official images from Hubble and other professional instruments show 3i Atlas as a blurred sphere surrounded by a coma, the expected cloud of gas and dust. They show a tail. They show what you would expect from a comet. But Craggs' image shows something else entirely. It shows structure where there should be chaos. It shows definition where there should be blur. It shows a glow that does not look like reflected sunlight bouncing off ice particles. It looks like something is being emitted, like something is on. This raises a question that feels almost dangerous to ask out loud. What if 3I Atlas is not a comet at all? What if what we are seeing is not a natural object, but something else? I want to be clear here. I am not jumping to conclusions. I am not saying this is an alien spacecraft. But I am saying that the difference between what professional observatories have shown us and what this backyard image reveals is so stark, so undeniable, that it demands an explanation. And right now, we do not have one. Comets have always occupied a strange place in human imagination. For thousands of years, they were seen as omens, harbingers of change, messengers from the gods. Then science came along and told us they were just ice and rock, leftover debris from the formation of the solar system. We demystified them. We turned them into predictable objects with well-understood physics. But every so often, a comet comes along that does not fit the script. And when that comet is not from our solar system, when it is a visitor from another star, the stakes become astronomically higher. Because if an interstellar object behaves in ways we cannot explain, it forces us to confront the possibility that our models are incomplete. Or worse, that something out there is intentionally defying those models. 3I Atlas is that object. It arrived from interstellar space, meaning it formed around another star, traveled for who knows how long through the void between stars, and then entered our solar system on a trajectory that will carry it past the sun and back out into the galaxy. It is a messenger from somewhere else. And now, thanks to Paul Craggs and his backyard telescope, we have an image that suggests this messenger might be more than just a chunk of ice. I want to take you on a journey over the next hour. We are going to compare this backyard image to the data from NASA's most powerful instruments. We are going to dig into the anomalies, the contradictions, the things that do not add up. We are going to ask the hardest questions, and we are going to explore the wildest possibilities, because sometimes the truth is wilder than anything we can imagine. This video will not give you easy answers. It will not wrap everything up in a neat bow. What it will do is show you why this matters, why this one object passing through our solar system might be the most important thing happening in space right now. So let me ask you this. What if the official narrative is missing something? What if the biggest telescopes in the solar system are showing us only part of the picture, and it took a small telescope in someone's backyard to reveal the rest? Over the next several parts, we are going to find out. And I promise you, the data we are about to examine will make you question everything you thought you knew about comets, about interstellar visitors, and maybe even about what is possible in this universe. Let's start with what the best instruments in the solar system have actually seen. Do they confirm what Craggs captured, or do they contradict it? That is where we go next. The story of 3I Atlas begins on July 1st, 2025, when a ground-based survey telescope in Chile, part of the Atlas network, picked up a faint smudge of light moving against the background stars. At first, it looked like just another comet, maybe a long-period visitor from the outer reaches of our solar system. But when astronomers calculated its orbit, they realized something extraordinary. This object was not bound to the sun. Its trajectory was hyperbolic, meaning it was moving too fast to be captured by our star's gravity. It was passing through, a visitor from interstellar space, only the third confirmed interstellar object ever detected after 1 I/Oumuamua and 2 I/Borisov. That discovery alone was enough to mobilize telescopes around the world. The official designation, 3I Atlas, tells you exactly what it is in the language of astronomy. The 3I means third interstellar object. Atlas is the survey that found it. From that moment on, every major observatory with a clear view of the sky started tracking it. Hubble turned its mirrors toward it. The James Webb Space Telescope locked onto it. Ground-based facilities across multiple continents coordinated observation campaigns. Even spacecraft in the inner solar system, Mars orbiters, heliophysics probes like Stereo-A and SOHO began collecting data. This was not just another comet. This was a solar system-wide observation event, the kind of coordinated scientific effort that only happens when something truly rare enters our neighborhood. The timeline mattered. 3I Atlas reached its closest approach to the Sun, called perihelion, on October 30th, 2025, at a distance of roughly 1.4 astronomical units, just inside the orbit of Mars. For context, Earth sits at 1 astronomical unit from the Sun, so this object came reasonably close by cosmic standards, but not dangerously so. After perihelion, it began its outbound journey, and according to current projections, it will make its closest approach to Earth around December 19th, 2025, at about 1.8 astronomical units, roughly 270 million kilometers away. That is still happening as we speak. The observation window is open, but it is closing fast. So what did all these telescopes actually see? The official data paints a picture of something that looks, at least on the surface, like a comet. Observations from Hubble and other facilities show a bright nucleus surrounded by a coma, the characteristic cloud of gas and dust that forms when ice sublimates in the heat of the sun. They see a tail, or at least the beginnings of one, made of gas and fine dust particles being pushed away by solar radiation and the solar wind. The spectral signatures match what you would expect from a comet. Water vapor, carbon dioxide, carbon monoxide, dust grains. All the usual suspects are there. By every conventional measure, 3I Atlas behaves like a comet. But even within that framework, there are oddities. The size of the nucleus, for example, remains frustratingly uncertain. Estimates place it somewhere between 440 meters and 5.6 kilometers in diameter. That is a huge range. In Earth terms, we are talking about an object somewhere between 1,400 feet and 3.5 miles across. Why such a wide margin? Because the nucleus is buried inside the coma, and separating the solid core from the surrounding gas and dust is extremely difficult, especially at these distances. The brightness we measure includes both the nucleus and the coma, and teasing those apart requires assumptions about reflectivity, composition, and activity levels. Get any of those assumptions wrong, and your size estimate shifts dramatically. The composition data is where things start to get interesting. Observations from the James Webb Space Telescope, using its infrared instruments, reveal that the coma is dominated by carbon dioxide. Not water, which is usually the primary volatile in most comets, but carbon dioxide. The ratio of carbon dioxide to water in 3I Atlas is among the highest ever measured for any comet, placing it well outside the normal range for objects in our solar system. Along with the carbon dioxide, there is water ice, carbon monoxide, carbonyl sulfide, and various dust particles, but carbon dioxide is king here. That is unusual. Solar system comets tend to be water-rich because they formed in regions where water ice was abundant. But 3I Atlas formed somewhere else, around another star, in conditions we can only guess at. Ultraviolet observations add another layer. Even at distances beyond 3 astronomical units from the Sun, far beyond where most comets show significant activity, 3I Atlas was still releasing water vapor. Telescopes detected hydroxyl emission, a telltale sign of water molecules breaking apart under ultraviolet sunlight. That kind of activity at such a large distance is rare. It suggests that the ice in 3I Atlas sublimates at lower temperatures than typical solar system comets, or that there is something about its structure or composition that makes it unusually active even when it should be dormant. So here is the scientific consensus as it stands today. 3I Atlas looks and behaves like a comet, just one that formed in another star system under different conditions. Leading scientists, including those at NASA and major research institutions, have stated clearly that there is no credible evidence of anything artificial or technological about this object. No signals, No anomalous accelerations that cannot be explained by outgassing. No structural features that scream engineered. It is a comet. Full stop. And yet, even among comets, 3I Atlas pushes the boundaries. The extreme carbon dioxide ratio, the size uncertainty, the unusual activity levels, all of these place it at the edge of what we consider normal. It is not breaking the rules, but it is bending them. And that is precisely what makes the backyard image so jarring. Because if this is just a comet, why does it look so different through Craggs' telescope? Why does the professional data emphasize blur and diffusion while the amateur image shows structure and clarity? Is it processing? Is it artifact? Or is there something about the way we are observing this object that is missing part of the story? That question brings us to the anomalies, the data points that do not quite fit, the measurements that make even skeptical scientists pause and wonder if maybe, just maybe, we are dealing with something we have never seen before. There is a moment in every investigation when the official story starts to crack, not because it is wrong, but because the details refuse to stay inside the lines. 3I Atlas is having that moment right now. The professional observations confirm it is a comet. Yes, but the data also reveals a collection of oddities that do not sit comfortably within the comet framework. These are not conspiracy theories. These are measurements from credible instruments, published in scientific papers, analyzed by researchers who have no interest in sensationalism. And they are strange. Let's start with one of the most bizarre findings: the polarimetric signature. Polarimetry is the study of how light becomes polarized or oriented in a specific direction when it scatters off surfaces or particles. When sunlight hits a comet's dust and ice, some of that light becomes polarized. And by measuring that polarization, scientists can infer properties of the particles, like their size, shape, and composition. Most comets show a predictable pattern. At small angles between the sun, the comet, and the observer, the polarization goes negative, meaning the light is polarized in a specific way. Then, as the angle increases, the polarization flips positive. This is called the negative polarization branch, and it is well understood. But 3I Atlas does not follow the script. A recent study of its polarimetric properties, conducted before it reached perihelion, shows a negative polarization branch that is both deeper and narrower than anything ever measured for a comet or asteroid. The polarization reached about negative 2.7% at small phase angles, with an inversion angle around 17 degrees. Those numbers might sound abstract, but here's what they mean in plain language. The way light is scattering off 3I Atlas is unprecedented. It does not match any known comet. It does not match any known asteroid. It suggests that the surface or the coma or both have physical or compositional properties that are fundamentally different from anything we have cataloged before. What could cause that? One possibility is that the dust particles in the coma are unusually small or unusually shaped. Another is that the surface has a texture or composition that scatters light in a non-standard way. A third option, and this is where it gets speculative, is that the outer layer of 3I Atlas has been altered by processes we do not fully understand yet. Processes that changed its optical properties in ways that no solar system comet experiences. Whatever the cause, the polarimetric data is a red flag. It is a signal that something about this object is off. Then there is the composition anomaly, which we touched on earlier but needs to be emphasized again. The carbon dioxide to water ratio in 3I Atlas is extreme. Most comets in our solar system have water as the dominant volatile, with carbon dioxide playing a supporting role. But 3I Atlas flips that script. Carbon dioxide dominates. The James Webb Space Telescope's infrared observations make this abundantly clear. That is not just unusual. it is a fingerprint of a different formation environment. It suggests that wherever 3I Atlas formed, water ice was less abundant, or carbon dioxide was more stable, or the thermal history of its parent system was radically different from ours. This object is telling us that not all star systems make comets the same way. The size and mass uncertainty compounds everything. Because we cannot pin down the exact diameter of the nucleus, we cannot accurately calculate how much gas and dust it should be producing for a given level of solar heating. If the nucleus is on the smaller end of the estimates, around 440 meters, then the observed outgassing requires an enormous amount of energy per unit area. The surface would need to be extraordinarily active, sublimating ice at rates that push the limits of what is physically plausible for a passive, sun-heated object. If the nucleus is larger, closer to 5 or 6 kilometers, then the numbers work out more comfortably. But we lose the constraint that could help us understand its structure and composition. This uncertainty is not just an inconvenience. It leaves room for alternative interpretations of what is powering the activity we see. Then, there are the morphological oddities, the shape and behavior of the coma and tail. Ground-based observations, some from professional telescopes, and some from skilled amateurs, report tail structures that are more complex than a simple single tail. There are reports of multiple jets, asymmetric jets that seem to shift direction over time, and even anti-tails, features that point toward the sun instead of away from it. Comets can produce these kinds of effects under certain conditions, usually due to the geometry of observation or dust particles of different sizes being pushed by solar radiation pressure at different rates. But the complexity here is high. The jets seem to turn on and off. The tail morphology changes. Some observers have noted that the brightness of the coma fluctuates in ways that are hard to explain with simple sublimation models. And here is where the energy budget question comes in. If the nucleus is small and the outgassing is as vigorous as some measurements suggest, then where is all that energy coming from? Sublimation of ice, the process where solid ice turns directly into gas, requires heat. That heat comes from the sun. But the amount of outgassing inferred from some observations seems high for the amount of sunlight hitting the surface. There are ways to explain this. Maybe the surface is darker than expected, absorbing more sunlight. Maybe there are subsurface pockets of volatile material that are venting suddenly. Maybe the rotation of the nucleus exposes fresh ice to sunlight at just the right times. All of these are plausible, but they are also post hoc explanations, adjustments to the model to make the observations fit. And when you start piling up adjustments, you have to ask yourself, are we explaining the data, or are we rationalizing it? One more thing. 3I Atlas passed perihelion, its closest point to the sun, in late October. But from Earth's perspective, it was behind the sun at that time. That means there was a critical observational gap during the period when the comet should have been most active. We missed the peak. We do not have continuous data. That gap leaves room for unknowns, for things that might have happened that we did not see. Maybe the comet fragmented and reassembled. Maybe it vented a huge amount of material all at once. Maybe nothing unusual happened at all. The point is, we do not know. And in science, unknowns are breeding grounds for speculation. So here is where we stand. The anomalies do not prove anything exotic. They do not prove 3I Atlas is artificial or technological, but they do prove that this object is not a typical comet, not by a long shot. The polarimetric signature, the carbon dioxide dominance, the size uncertainty, the complex jets, the energy budget questions, all of these are real data points from credible sources. They challenge the purely natural, purely boring interpretation. They demand a closer look. And they set the stage for a hypothesis that attempts to reconcile the strangeness without invoking aliens. The idea that 3I Atlas is not just an interstellar comet, but a processed interstellar comet, shaped and altered by its long journey through the void. That is where we go next, into the science of cosmic radiation and what it does to objects that spend millions or billions of years traveling between the stars. There is a way to explain the strangeness of 3I Atlas without invoking anything sensational, and it involves one of the most relentless forces in the universe: galactic cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, that zoom through interstellar space at nearly the speed of light. They are everywhere. They are constant, and they do not care what gets in their way. For objects like 3I Atlas, which likely spent millions or even billions of years drifting through the galaxy before entering our solar system, cosmic rays are not just background noise. They are a transformative force. Recent modeling by planetary scientists suggests that long-duration interstellar travelers undergo a process called cosmic ray processing. Imagine a comet nucleus, a frozen ball of ice and rock floating through the void. Over time, cosmic rays bombard its surface, penetrating the outer layers and depositing energy. That energy breaks chemical bonds. It rearranges molecules. It converts simple compounds into more complex ones. Carbon monoxide can be transformed into carbon dioxide. Organic molecules can be synthesized. Water ice can be altered or destroyed. The result, after enough time, is a surface layer that looks and behaves nothing like the pristine ice that formed in the original star system. It is a crust, a chemically processed skin, shaped by radiation rather than by heat or collisions. This is not speculation. We know cosmic rays do this because we see similar effects on objects in our own solar system. Small bodies in the outer solar system, like Kuiper Belt objects, show spectral signatures consistent with radiation processing. Meteorites that have spent time in space carry evidence of cosmic ray exposure. The physics is well established. What is new is the realization that interstellar objects, which travel for vastly longer timescales and at much higher speeds relative to the galactic cosmic ray background, experience this processing on a completely different scale. By the time 3I Atlas entered our solar system, its outer layers may have been thoroughly cooked by radiation. This hypothesis aligns surprisingly well with the observed data. The extreme carbon dioxide to water ratio in the coma. That could be the result of cosmic rays converting carbon monoxide, rich ices, into carbon dioxide over time. The red spectral slope observed by spectroscopy, which suggests the presence of complex organic compounds. That could be radiation-synthesized organics, the byproducts of millions of years of high-energy particle bombardment. The unusual polarimetric signature, that could come from dust and ice particles with altered textures and compositions, scattering light in ways that no solar system comet does, because no solar system comet has been exposed to the same level of processing. According to the models, the current outgassing we are seeing from 3I Atlas likely samples only the top 15 to 20 meters of the processed layer. That is important. It means we are not seeing the original material, the pristine ice that formed in whatever star system gave birth to this object. We are seeing the product of its journey, the result of eons of radiation exposure. The interior, the deep ice buried beneath the crust, might be completely different. It might be water-rich. It might have a different isotopic composition. But we will never know unless we can somehow dig down, or unless the comet fragments and exposes fresh interior material. The implications of this are profound. If cosmic ray processing is a common phenomenon for interstellar objects, then every interstellar comet we catch is not a clean snapshot of another star system. It is a weathered traveler, modified by its journey. It is like finding an ancient artifact that has been buried, eroded, oxidized, and chemically altered by its environment. The artifact is real, but the surface you see is not the surface it had when it was made. Applying that analogy to 3I Atlas, the comet we are observing today may tell us more about the interstellar medium and cosmic radiation than it does about the star system where it formed. This raises a fascinating question. Could processed interstellar comets constitute an entirely new class of small bodies? Not comets in the traditional sense, and not asteroids either, but something in between, defined by their radiation history rather than their formation history. If so, then we need new frameworks for understanding them. We need new models for predicting their behavior. And we need to reconsider our interpretations of past interstellar visitors, like 1I/Oumuamua, which was famously strange, and 2I/Borisov, which seemed more comet-like. Maybe they were all processed to different degrees, and that is why they appeared so different. But the cosmic ray processing hypothesis, compelling as it is, does not close the case. It explains some things well and others less so. For example, it does not easily account for the structural stability of 3I Atlas. If the outer crust is heavily processed and possibly weakened by radiation damage, why has the comet not fragmented yet, especially after passing close to the sun where thermal stresses would be highest? Comets fragment all the time. They are fragile. They break apart under much less stress than 3I Atlas has experienced. Yet, as far as we can tell, this object is still intact. That suggests either the nucleus is more robust than expected, or there is something about its internal structure that provides unusual strength. There is also the issue of the jets and the outgassing asymmetry. Cosmic ray processing might alter the composition of the outer layer, but it does not necessarily explain why the outgassing appears to be so active, or why the jets seem to shift and change over time. Those behaviors suggest active venting, possibly from subsurface reservoirs of volatiles that are suddenly exposed, or from rotating active regions on the nucleus. The processing hypothesis helps with composition, but does not eliminate the need for a more detailed understanding of the nucleus's structure and rotation. So where does that leave us? The cosmic ray processing model offers a compelling middle path between the mundane and the sensational. It says 3I Atlas is not just a boring comet, but it is also not an alien ship. It is something new, a category of object we are only beginning to understand. It is a messenger, not just from another star, but from the journey between stars, carrying information about one of the harshest environments in the universe. That is valuable. That is worth studying. But it is also provisional. Like all scientific hypotheses, it is subject to revision as new data comes in. In the next few months, as 3I Atlas continues its outbound journey and we gather more observations, could either solidify this model or blow it wide open. Either way, we are watching something unprecedented unfold in real time. Now let's talk about the other interpretation, the one that makes scientists wince and internet forums light up. There is a growing contingent of observers, mostly outside the mainstream scientific community, who argue that the comet model does not just have holes. It is fundamentally wrong. They look at the same data we have been discussing, the same anomalies, the same backyard images, and they arrive at a radically different conclusion. They say 3I Atlas is not a natural object. They say it is artificial. They say it might be a probe, a ship, or debris from an extraterrestrial craft. Let's walk through their arguments, not to endorse them, but to understand them. The starting point is often that backyard image from Paul Craggs, the one showing a clean, structured object with a sharp white fuselage and a blue glow. To proponents of the alternative hypothesis, this is not processing artifact or over-enhancement. This is raw data revealing what the object actually looks like when you strip away the assumptions. They argue that professional telescopes are calibrated to expect diffuse, fuzzy comets, so they blur and smooth the images to match that expectation. But when you use a smaller telescope with less pre-processing, you see the truth, a defined, engineered shape. Some claim there is no tail, or at least Not the kind of chaotic dust tail you would expect from a fragmenting comet. Instead, they see a tight, uniform glow that they interpret as some kind of emission, perhaps an energy field or exhaust plume. Others point to reports, mostly from amateur observers and fringe researchers, of non-gravitational accelerations that are too large or too consistent to be explained by outgassing alone. In comet physics, outgassing can push a comet slightly off its predicted orbit because the jets of gas act like tiny rocket engines. But the magnitude and direction of those pushes should be irregular and tied to the rotation of the nucleus. If the accelerations are too smooth or too sustained, it raises the question: is something else providing thrust? Then there is the trajectory argument. Some proponents claim that 3I Atlas's path through the solar system is not the random wandering of a rogue comet, but a deliberate route, possibly designed for reconnaissance or for deploying smaller probes. They note that after passing the Sun, its trajectory will carry it on a long arc that could, in principle, bring it near Jupiter in the future, though that depends on precise orbital calculations that are still being refined. To them, this is not coincidence. It is intentionality. These ideas are not coming out of nowhere. They are fueled by a broader cultural moment where the possibility of extraterrestrial intelligence is being taken more seriously than it has been in decades. Recent government acknowledgments of unidentified aerial phenomena, or UAPs, have opened the door to mainstream discussions about non-human technology. The idea that an interstellar object could be a probe is no longer dismissed outright by everyone. Even some scientists have speculated, cautiously and hypothetically, about what a technosignature from an interstellar visitor might look like. 3I Atlas, with its anomalies and its striking appearance in amateur images, has become a lightning rod for those ideas. But here's the problem. The mainstream scientific community, including space agencies and leading researchers, has looked at the same data and found no credible evidence of anything artificial. No signals, no anomalous materials, no structural features that cannot be explained by natural processes. The jets, the outgassing, the coma, the tail, all of it fits within the bounds of known comet behavior, even if it pushes the edges. The polarimetric oddity, the composition anomaly, the size uncertainty, all of these are unusual, yes, but unusual does not mean technological. It means we need better data and better models. The alternative hypothesis, compelling as it might seem to some, currently lacks the extraordinary evidence needed to support such an extraordinary claim. There is also the question of perception and processing. The human brain is extraordinarily good at seeing patterns, even when they are not there. This is called pareidolia, the tendency to perceive meaningful structure in random or ambiguous stimuli. It is why we see faces in clouds, animals in rock formations, and yes, spacecraft in blurry images of comets. When you are primed to look for something artificial, your brain will find it. Amateur images, especially those that have been heavily processed, stacked, and enhanced, can introduce artifacts that look like structure, but are actually noise or compression effects. This does not mean Craggs' image is fake or deliberately misleading. It means we have to be cautious about interpreting it without rigorous calibration and peer review. The appeal of the alien hypothesis is obvious. It taps into one of humanity's deepest questions. Are we alone? The idea that an interstellar visitor could be a messenger from another civilization is thrilling. It is the stuff of science fiction made real. It resonates emotionally and culturally in ways that a processed comet does not. And that is precisely why it spreads so quickly, and why it needs to be scrutinized so carefully. Extraordinary claims demand extraordinary evidence. Right now, the evidence for 3I Atlas being artificial is circumstantial at best. It rests on ambiguous images, contested interpretations, and gaps in the data that leave room for speculation. But here is the intellectual challenge, and it is a fair one. Could a natural object ever plausibly look ship-like under certain observational conditions? Could the interplay of jets, dust, geometry, and lighting create an appearance that mimics structure? If so, how would we distinguish between a natural object that looks artificial and an actual artificial object? That is not a trivial question. It is the kind of question that serious scientists have to grapple with, especially as our observational capabilities improve and we start detecting more interstellar objects. We need criteria, specific testable predictions that would allow us to say, definitively, this is natural or this is not. And here is the flip side. If 3I Atlas were a probe or a ship, how would we prove it? What would the smoking gun look like? A radio signal? Anomalous materials detected spectroscopically? A maneuver that defies orbital mechanics? All of these are possibilities, and all of them are being looked for, whether officially or unofficially. The next few months could provide answers, or they could provide more ambiguity, which is often how science works. Either way, the question has been raised, and it will not go away quietly. Whether 3I Atlas is a comet, a processed comet, or something else entirely, it has forced us to confront the limits of our models and the vastness of what we do not yet know. And that uncertainty, as uncomfortable as it is, might be the most important thing this object teaches us. 3I Atlas is not standing still. It is hurtling through the solar system right now, and the clock is ticking. This is a one-time event, a single pass through our neighborhood before it vanishes back into interstellar space, possibly forever. According to current orbital projections, the comet will make its closest approach to Earth around December 19th, 2025, at a distance of about 1.8 astronomical units, roughly 270 million kilometers. That is happening soon. The observation window is still open, but it will not stay open for long. Every day that passes, 3I Atlas moves farther from the sun, grows fainter, and becomes harder to study. If we are going to get answers, we need to get them now. The good news is that astronomers are mobilizing. Ground-based telescopes, space-based observatories, and even spacecraft in the inner solar system are all pointed at this object, trying to extract as much data as possible before it slips away. The goal is not just to confirm what we already think we know, but to look for the unexpected, the details that could discriminate between competing hypotheses. Is this a normal comet, a processed interstellar traveler, or something else? The next few months of observations could provide the clues. One of the highest priorities is to resolve the nucleus itself. Right now, all we see is the coma, the cloud of gas and dust surrounding the solid core. But if we could image the nucleus directly, we could measure its actual size, shape, and surface features. That would tighten the uncertainty around mass, density, and composition. It would also tell us if the nucleus is a single coherent object or a loose rubble pile, which affects how it responds to thermal stress and outgassing. Large ground-based telescopes equipped with adaptive optics, which correct for atmospheric distortion, are attempting this right now. They are looking for brightness variations that could indicate rotation or irregular shape. They are searching for any hint of fragmentation or satellites, smaller pieces that might have broken off. Multi-wavelength campaigns are also underway. Optical observations give us the visible structure and dust content. Infrared observations, like those from the James Webb Space Telescope, probe the composition of the gases and ices. Ultraviolet observations detect emissions from water and other volatiles. Radio and radar observations, if the geometry allows, could reveal thermal signatures or even surface roughness. By combining data across the electromagnetic spectrum, scientists can build a more complete picture of what 3I Atlas is made of and how it is behaving. One of the most critical measurements is tracking non-gravitational accelerations. As the comet outgasses, the jets of escaping gas exert tiny forces on the nucleus, nudging it off its purely gravitational trajectory. By comparing the predicted orbit, calculated using only gravity, with the actual observed position over time, astronomers can measure these accelerations. For a normal comet, the accelerations should correlate with outgassing activity. They should vary with distance from the Sun. They should change as the nucleus rotates, and they should fade as the comet moves farther out and becomes less active. If the accelerations are sustained, constant, or uncorrelated with expected outgassing patterns, that would be a red flag. It would suggest that something other than sublimation is affecting the orbit. Polarimetric studies are continuing as well. The unusual negative polarization branch detected before perihelion needs to be followed up. Does it persist as the geometry changes? Does it evolve as the comet moves farther from the Sun and the coma thins? Polarization is sensitive to the size, shape, and composition of dust particles, so changes over time could reveal whether the dust is coming from a static surface or from deeper layers with different properties. If the polarization signature shifts dramatically, it could indicate that the comet is shedding its processed outer crust and exposing fresh material underneath. The morphology of the coma and tail is also being monitored closely. Scientists are looking for jets, anti-tails, and any asymmetries that could reveal active regions on the nucleus. They are measuring how the brightness changes over time, looking for periodic patterns that would indicate rotation. They are trying to map the distribution of different gases, like carbon dioxide and water, to see if they are coming from the same regions or from different parts of the surface. All of these details help constrain models of the nucleus's structure and activity. So what would it take to challenge the comet model? What observations would make scientists sit up and say, wait, this does not fit? Here are a few possibilities. Sustained non-gravitational acceleration without corresponding mass loss. If the comet is accelerating but not losing enough gas to account for that acceleration, something else is pushing it. A symmetric, geometric shape that persists over time. Comets are irregular because they form through accretion and erosion. A perfectly smooth or symmetrical object would be suspicious. Unexpected spectral lines. If observations detect emissions from metals, refractory materials, or compounds that should not exist in a comet, that would demand an explanation. Anomalous thermal emission. If the object is too hot or too cold for its distance from the Sun, that suggests an internal heat source or unusual thermal properties. Stability despite heavy activity. If the comet is venting enormous amounts of gas but shows no signs of fragmentation, erosion, or structural change, that implies unusual strength or an engineered structure. None of these have been observed yet. But the key word is yet. The observation campaign is ongoing, and new data is coming in regularly. If any of these telltale signs appear, they will be noticed. The challenge is that 3i Atlas is getting fainter and harder to observe as it moves away. By early 2026, it may be too faint for all but the largest telescopes. If the data quality drops before critical questions are answered, we may lose the chance to know for sure. There is one more possibility, a long shot but worth mentioning. If someone detects radio emissions, periodic pulses, or structured signals that cannot be attributed to natural processes, that would be paradigm-shattering. Organizations like the CD Institute are listening. If 3i Atlas is transmitting, someone will hear it. But the absence of a signal does not mean anything. A probe designed to be stealthy or simply inactive would not broadcast. Whether 3i Atlas turns out to be a weird comet, a processed interstellar traveler, or something more exotic, documenting it thoroughly matters. This is our best chance in decades, maybe centuries, to study an interstellar object up close. The next visitor might not come for another 50 years. The next visitor might be too faint to observe. This is the moment. So to astronomers, amateurs, citizen scientists, and anyone with access to a telescope, watch the sky. Keep probing. record everything. Because this might be the cosmic guest that forces us to rewrite the book. And if we miss it, we may never get another chance. Let's step back and ask the biggest question. Why does any of this matter? Why should you care about a chunk of ice and rock, or whatever it is passing through the solar system? Because 3I Atlas is not just another comet. It is a messenger from another star, and every detail that does not match our expectations is a clue about the universe beyond our solar system. This object is teaching us, whether we like it or not, that our models are incomplete, that the diversity of small bodies in the galaxy is far greater than we imagined, and that the cosmos is stranger and more varied than we ever gave it credit for. 3I Atlas is expanding our taxonomy of what exists. For decades, we have categorized small bodies in our solar system as either comets or asteroids, with some gray area in between. Comets are icy, active, and form in the outer solar system. Asteroids are rocky, inert, and form in the inner solar system. Simple, clean categories. But interstellar objects do not fit. They formed somewhere else, under different conditions, around different stars, and they spent millions or billions of years traveling through the interstellar medium, exposed to cosmic radiation, interstellar dust, and who knows what else. By the time they reach us, they are not pristine snapshots of their birth systems. They are products of their journeys, altered and processed in ways we are only beginning to understand. If the cosmic ray processing hypothesis is correct, and the evidence strongly suggests it is at least part of the story, then 3I Atlas represents an entirely new class of object, not a comet in the traditional sense, not an asteroid, something else, a processed interstellar traveler. And if one exists, there must be more. The galaxy is full of stars, and stars make planetary systems, and planetary systems eject material. Some of that material ends up wandering through interstellar space, getting cooked by radiation, until it stumbles into another star system. We are starting to realize that interstellar visitors might not be rare anomalies, but a regular feature of the galaxy. We just did not have the technology to detect them until recently. The science implications are enormous. Studying objects like 3I Atlas gives us insights into planet and solar system formation in other stellar systems. The composition of the ice, the ratio of volatiles, the presence of organics, all of these tell us about the conditions in the protoplanetary disk where the object formed. Was water abundant? Was carbon dioxide more stable? What was the temperature profile? What kinds of chemistry were happening? These are questions we cannot answer by studying our own solar system alone, because our solar system is just one data point. Interstellar objects give us comparison points, allowing us to test our models against a broader sample. There is also the question of cosmic radiation itself. 3I Atlas is a laboratory for studying what happens to material exposed to galactic cosmic rays over timescales we can never replicate on Earth. The surface chemistry, the dust properties, the altered ices, all of these are records of that exposure. By decoding them, we learn about the interstellar medium, the radiation environment between stars, and how matter evolves over cosmic time. That knowledge feeds into our understanding of everything from star formation to the origins of life. Because the organic molecules that seed planets and possibly biology are also shaped by these processes. And then there is the philosophical dimension. What does it mean for humanity's place in the cosmos if we start cataloging objects from other star systems with chemistries, histories, and properties we never anticipated? It changes our sense of scale. It reminds us that our solar system is not a template for the universe, but one example among billions. The ice that makes up 3I Atlas formed around a star we will never see, in a system we will never visit, under conditions we can only infer. And yet, here it is, passing through our neighborhood, close enough for us to study. That is humbling. It is also exhilarating. Looking forward, the technological and observational landscape is shifting in our favor. Ground-based surveys, like the Vera C. Rubin Observatory, which will begin full operations soon, will detect interstellar objects earlier and more frequently. Space-based telescopes, like the James Webb Space Telescope, Nancy Grace Roman Space Telescope, and future missions will provide the spectral and imaging capabilities to study them in detail. We are entering an era where interstellar visitors will not be rare curiosities, but regular subjects of study. In the next few decades, we may catalog dozens, maybe hundreds, of interstellar objects, each with its own story, its own chemistry, its own journey. 3i Atlas might be the first of a new wave, or it might remain an outlier, a one-off anomaly that defies easy categorization. Either way, it has already changed the conversation. It has forced scientists to confront the limits of existing models and to develop new frameworks for understanding objects that do not fit the old categories. It has engaged the public, sparked debates, inspired backyard astronomers to point their telescopes at the sky and capture images that challenge the official narrative. It has reminded us that space is not empty, that the galaxy is alive with debris and messengers, and that sometimes the most important discoveries come not from billion-dollar missions, but from curious individuals asking, "What is that?" If there is one lesson 3i Atlas teaches, it is humility. We think we understand comets. We think we know what to expect from interstellar visitors. But every time we test those assumptions against real data, the universe surprises us. It shows us something we did not predict, something we did not think was possible, something that forces us to revise and expand our understanding. That is how science works. That is how knowledge grows. Not through confirmation of what we already believe, but through confrontation with what we did not expect. So here is my final question for you, the one that will linger long after this video ends. When the next interstellar visitor arrives, and it will arrive, will we recognize it? Or will it slip past us because it does not fit our expectations? Because it looks too strange, too clean, too different from what we think an interstellar object should be? 3i Atlas has taught us to look harder, to question more, to hold our assumptions lightly. It has taught us that the universe does not owe us familiar answers. Sometimes the messenger is the message, and sometimes the message is simply this: you do not know as much as you think you do. Stay curious, stay skeptical, and keep watching the sky, because the next impossible thing is already on its way.